All right. Good morning, everyone. Sorry, I'm a little bit breathing in and out. Had to run up to my office to get my second laptop here, so catching my breath. Okay, so today we're going to continue and hopefully finish our terrain exercise. Before I really jump in, I just want to ask, like, is anyone still having or is having issues with the script? Any questions you may have about what we covered?
I had an issue on the very last section and I had to hop off right at 10 on Friday, the slope section
Okay.
with the dplyr. It just doesn't run for me. It says unexpected symbol.
You want to share your script before or your screen?
Yeah, I can do that. Does that work?
Yes.
Yeah, it doesn't like this little segment right here. I'm not sure why.
Oh, okay. So I think what's going on. So, this is a good, I always like when any of us really, including me, run into errors, because the one thing for sure you're going to have when you're programming is you're going to run into errors. So I think it's a great exercise to just, take a look at this and try to see how would we even realize what's going on. So normally, but not always, the error messages that we get, maybe I should say not normally. Most of the time, the error messages we get are not very informative of what's going on. They just say error and say some weird cryptic thing that's going on behind the scenes that to us doesn't make sense. However, in this case here, it's not clear cut, but I think it can help us to understand what's going on. So if we just go through this, I was saying error, unexpected symbol in, and then it basically stops that message there right at where it was struggling with. So I will perhaps ask, either you, Sarah, or really anyone else, if anyone can spot what's going on. If anyone has any.
Sid forgot the lowercase between the elevation and then it seems like it's two different elements, which should be just one.
Yes, I think that's the issue too. I don't know if you guys were able to. So if you notice, there's a white space in between 11 and M. And yep, right there. And if we look into the data set, the name of that column is 11_M. So just because we're missing that underscore is saying that it doesn't know what that is. Yep, there we go.
So easy.
Yeah, and in this case, it wasn't super clear from the error message, but at least it was telling us where exactly was happening. So if we look around there, we could kind of figure out. And that's, partially one of the reasons why we don't use space in column names is that, I mean, not directly that, but just because if you can use a space in column names, but it makes a little bit more difficult to code, because we have to add like apostrophes. So we don't want to do that all the time. So that's why if I want to add, if in my head I'm trying to add a space, I actually replace that with underscore, or sometimes a period also works. But in this case, and I'm showing you guys to use underscore throughout, but those are just different styles of programming. Yeah, but so yeah, that was it. It was a pretty simple problem, I guess. But yeah, it's a great exercise to try to troubleshoot things. And maybe depending how much time I still have with you guys this semester, maybe we will have a class just in troubleshooting. I'll send you guys only code that doesn't work and ask you guys to see if you can fix it. That would be a great exercise.
That's a great idea, because what Sarah's experiencing is my constant problem. It's I make a typo, and then because I've made the typo, it's very difficult to find it, to go back.
Yeah.
Spend a lot of time just chasing that one typographical error.
Yeah, I'm gonna think about it and see with George if I have more time that I can spend with you guys, maybe one class and one homework just on troubleshooting code. Because that is a really important skill that most of the time we learn because we have to, not because somebody taught us.
Thank you.
Yeah, no problem. All right, so anyone else, any questions, any problems? All right, I'll take that as a no, and I'll start sharing my screen again. So as usual, I just want to show you where I'm starting off and not just show you already the RStudio window opened, so you can see my path of getting there. So, this is again this is actually my project. Let me take a step back here and go to my overall course folder where I have my project right there with my initials. So I go into that. You guys should be seeing the structure here that we've been using from the beginning. I'm just going to launch my project right here. Make this screen here smaller. So for me, it opened my project. And again, how do we know that we are in the right project? We have to see the project name up there on the right. Especially if you're seeing project none, it means you're not in any project, and that is something that we should address. But at this point, I think you guys should all be seeing your project initials up there. And for me, already showed me the script here. So the partial script for the terrain exercise. For me, I'm not seeing any variables in my environment, which is something that I personally like. I know that sometimes people like to, when you close RStudio, you like to save your environment variables. So when you reopen that project, they're there already. I really only recommend that if one of your objects is big and takes time to create, So if you're doing if you have an object that is an interpolation result that takes you half an hour to run that code, yes, that would make sense to save that object in your environment and reload it afterwards. But if it's quick things that you can just rebuild again from the code, I would recommend to not save your environment when you close RStudio, because that can create some ghosts in your, and this is kind of the terminology people use, is create some ghost objects in your environment that sometimes you made some changes, but then you're not sure. Some issues can arise from that, just from the fact that you have some past versions of your objects coming in already, and you may not know if they're the finished versions or not. Anyways, so on the first, or on our last meeting here, we went all the way through slope, right? So we finished here pretty much on the slope map. And today we're going to start with aspect. What I want to ask you to do, if you don't have your objects created, like I don't in this case, instead of having you go through and clicking the play button on each chunk that is above where we're starting today, there's a quick trick to that if you come to the chunk that you're going to be starting today, so this first chunk here in aspect, this button here basically runs all the chunks above it, but not including it. So we can just hit this button here if you have not, and then you can see that there is a green progress bar on the bottom showing me the overall progress. I see the objects being created up here, and the code, as the chunks are being run, the code, the green bar appears right next to that chunk. This is a nice and quick way of just, getting you up to speed with whatever point we stopped. The one thing that I should say is, if you do use this shortcut, if you have left any errors on any chunks above in your code, those errors are gonna stop pretty much this process of just running everything through automatically, and you're not gonna get to the end of where you thought you were gonna get to. So just to keep that in mind, in my case, I didn't leave any lingering errors above, so I was able to, everything ran nicely. I got all my outputs here, all my objects, and then we can just really start at the point of aspect. Okay, so I left you here almost the complete code for aspect. And the main reason for that is it's pretty much the same code as we did for slope. The only difference is right here where I just left 3 dots there, which is not code, it's just to remind me that we have to fill in that gap with actual code. So if you recall, I'm just going to come up. You can stay on your aspect code. I'm going to go up to my slope code, so you can see here. So we started with the data set, and then we selected the variable. We used the rest function just to transform this stars object into the spat raster object that is needed for the terrain function. So this is really the function that I removed from below, from the aspect code. So just wanted to show you that this is what is missing. And you can copy and paste if you want. I would rather much just come here and type, so we get used to typing these functions. So it's coming again from the package Terra, and when you want to specify the package that a function is coming from, you use this notation. So package name : and the function name is terrain. So here, the only difference really is that the first argument, where before we had slope, here's going to be aspect. And then I just want to change the unit. So you say unit equals radians, just because the default is in degrees. So we're just going to change to radians. And if you run this, it should run nicely. And then when we print this object here, it should be a stars object. And so again, we start with a stars object with the IDW pred. We transform that to spat raster object to apply the terrain function. And then we bring it back to a stars object with the function st as stars, just so we can use it with our framework of ggplot, and then we print it. So we see here, the values ranging from what we see here, 0.0007 all the way to 6.28, and this is in degrees radians. And if we come on the second tab here, we see that is in the proper CRS that we've been working with consistently. So that's all great. I also left you the plot here, the plot code, because we developed this code here for the slope part of it, line by line. And I just didn't want to make you go through everything again, just really changing here. The 2 things we're changing is the data for the geom stars. So before it was slope, now it is aspect. And also the label for the fill aesthetics, I changed to aspect, and before it was slope. So that's really the only difference. If you run and you print it, you can see a map of aspect, which I guess perhaps is because of the resolution that we selected. This map is not really easy to tell what's going on, but it is going to be important for when we do the hillshade, and you're going to understand better when we get there. Okay, so we have our elevation map, our slope map, and our aspect map.
Leo, I think maybe if you could define what aspect means. I'm not sure that everybody knows what it means in terms of terrain.
Yeah, so aspect would be pretty much the orientation. So if you think of slope, right, you have a slope, but then the slope by itself doesn't really tell you where that slope is facing. You can have the same value of slope, but facing different directions, right? So aspect brings you that information of where, what is the degree that that slope is facing. So that this is pretty much what aspect is.
That has a lot of uses in precision ag. I mean, what we're doing now is one use, but a lot of times on really big fields with bigger slopes, it might be important to find which way slopes are facing, because that will affect, for example, wheat yield in rain-fed conditions. It affects what kind of precipitation some areas might receive based on the aspect, north facing, south facing, east facing, west facing, and so on. So it's a really good way to be able to look at, to try to explain what might be happening with yields sometimes.
Yeah, and that was perfect compliment as well, George. And I guess I wasn't spending too much time looking at this map because at least for me, it's not very clear what's going on with the aspect here. But we're going to calculate hillshade and in the next chunks here. And hillshade really, it takes into account both the slope and aspect, and also the degree of which sunlight would be hitting the terrain, and uses all those three pieces of information to create a hillshade map. So if you haven't seen what hillshade map is, we're going to be seeing next. And I think that one is going to be a lot more clear to really show. And again, for some reason, maybe it's our spatial resolution that we selected, or I don't know. For me, at least personally, looking at this specific aspect map, it's not very clear, at least not throughout.
Well, I think it's really typical of the field. I mean, it's, you know, there's a gentle slope running from west to east, but there's not a lot of, you know, hill action, for example, there that you could visibly see with the naked eye. You know, there's gentle slopes with some depressions, but it's not something that, like, you know, hillsides in Montana or up in the Piedmont,
Right.
Of Georgia fields or something like that. That's why it's a little confusing.
Yeah, absolutely.
Dr. Bastos,
Yes.
is it possible to say that you can give an example from this only map how we can interpret the direction of the slope?
So yeah, so it's kind of based on that color change, right? So if you see here, I mean, it's again, it's not super clear just because, you know, it's not a very, it doesn't have too much of a difference, but you can kind of see how the shaded areas change around this area, perhaps especially, and you would kind of have an idea of like where that slope is facing. But again, I think it's going to be more clear for us to see when we get to the hillshade part, and then we can spend more time discussing that, if that's okay. Because you know, because to get to hillshade, we need both slope and aspect. So I really wanted to show you guys the output of that, but I think it's going to be more clear for us to discuss on the hillshade map when we get to that point.
Okay, thank you.
Yeah. Okay, so the next one that I wanted to show you here is flow direction. And again, it's same code as for slope and aspect. There's just one difference there. I just want to ask you to go on those three dots, and we're just going to change that. You can delete that. And again, the package name is Stera. We're calling the function terrain from that package. And this argument, the first argument, is what's going to be different. So you can just open and close quotation marks, and then we're going to call flow dir for flow direction. And again, just for sake of consistency, I want to say unit, or sorry, units in singular equals radians. And don't forget to add the pipe at the end of it, so it connects with the remaining. So we can just run that. I again will quickly just print below here. Mostly two things I'm looking for in here is on the first pane, I just want to take a look at especially the minimum and maximum value. And then making sure on the second pane that it is in the correct CRS that we've been using. And both of them match, so they're good to go. Just gonna come over here and we can print this. So this again is, oh, I have degree here. I have to check. I'm not sure. I don't, now that I'm thinking, I don't know if flow direction actually takes this unit radians. Maybe it doesn't, because we see the values being very high. I think this is actually degrees in this case specifically for flow direction. And we can kind of see how, you know, it's basically just giving us an indication of what degree in that terrain would water be flowing into or out of. So we do see this, the darker regions here would be a lower degree, and then just going higher degrees with a like a white color. And, again, this way of calculating flow direction to me is not very intuitive as well. Just looking at this, there are some different ways of calculating this. I wanted to show you guys using the terrain function just because we're already within that function, just changing the arguments to get different information. But just visually as well, in thinking of degrees is a little bit difficult as well for my head, at least to understand what is actually going on this map. I don't know if anyone else has experience working with flow direction in your research, that you would have some more insights. Yeah, I guess it's going to get a lot more clear when we look at the hillshade. And again, flow direction is not an input to calculating hillshade, but it was an easy variable to calculate here that I just wanted to show you. And also to remind you that this function terrain that we're using to calculate these terrain variables, if we just go again on the help, ask for help of that function, so help terrain, it has even more variables that I'm not showing you how to use here. It has some different indices. So if we come, so I just asked for the help, and then I'm just coming here on this V, which is the argument that we're changing when we're specifying different variables. We see here that it takes one or more of these options: slope, aspect, TPI, TRI, roughness, flow direction. So I'm not showing you roughness, TPI, or TRI, but these are things that, some papers use these variables, some people use these variables. And I just wanted to show you that if you wanted, you could calculate those with the same code pretty much, just changing this argument here. And if this is your research and you're really trying to explore things, maybe you would like to calculate all of those and include in your final analysis. Here, I just decided to show you elevation, slope, aspect, flow direction, and hillshade. Okay, so this is our flow direction map. Now let's get to hillshade. So as I was telling you, hillshade is going to use both slope and aspect, and then it takes an argument to define what is the angle of the sun that we want to calculate hillshade for. So that's what we're going to be doing here, but and we have to do some coding before getting there. So the hillshade function comes as well from the Terra package, from the function terrain, which again, it requires the object coming in to be in that spat raster class. And if you recall throughout, I'm just going to show you for flow direction because it's the closest one, even though we're not using flow direction, but we're starting with a stars object. We're transforming that to spat raster using the terrain function, and then transforming back to stars, meaning that we need again an object of slope and aspect back on that spat raster class, which right now we have as stars. So we're going to just do that transformation quickly here, starting with slope. So we use that assign symbol. Slope, again, is the object name where we have the slope, and it is a stars object. I'm just printing here. It is a stars object, so you can see. We add a pipe here, and then there's this function called as. It's just as like that. And then you open and close quotation marks, and we say raster. And I don't know if it makes a difference if we have this R lowercase, but I have it uppercase. So if you just want to do that, and this is going to be, it's going to be really interesting because if we just do this, that transforms slope into first raster. So sorry guys, I know this can be a little bit confusing, and I'm just going to try to walk you through what's going on. So slope is a stars object. We're transforming that into a raster layer, which is the type of object when we work with functions from the package raster. Okay, so I'm just going to write here a comment just so you can see. So the stars package, right? So stars package. We have the raster package, and we have the Terra package. These three packages all work with raster objects. However, each one of them has a different object type to refer to a raster, right? So a stars package creates a stars raster object. The raster package creates a raster layer object, which is what we have at this point here, just transforming to raster. And the Terra package has a spat raster object. So you see that 3 different packages, they all create different types of objects, even though they all are rasters. And this is one of the things that we see a lot in programming languages, is that different people creating different packages for similar applications end up with different object types. And the main thing that happens there is that some functions only work with some of those object types and so on. The good thing is that they are interchangeable. You can start with one, transform to the other types fairly easily. So here, we're first transforming slope into the raster layer, and then we're taking the step to transform it to the spat raster. And I don't recall now when I was developing this code why we had to go stars, raster, Terra. I think there was something very specific about it, that if I just went straight from slope to rast, it would not work the way I intended. That's why we're basically doing 2 transformations back to back here. So we're gonna pretty much repeat this. So now we're ready. So if you just run that and you print slope SPV, now we see that it is a spat raster, which is what we need to do the hillshade. And we just did that for slope. Now we need to do the same steps for aspect. And we're gonna save on this object here. We're starting with this, our object called aspect, which is our stars object. Let me just show you again, it is a stars object. I'm just gonna do the same. So as raster, then pipe rest. The same as we did above. If you just run this, you're gonna, and you print just that aspect SPV, we see now that it is a spat raster object coming, or that is native to the Terra package. Okay, so now we do have both slope and aspect in that spat raster class, which is needed to do the hillshade. So let's do the hillshade next here. It's going to be on this, we're going to save that to an object called hill. We use the assignment symbol, and then the function is called shade. It's coming from the Terra package. So pretty much what we do here is we give that slope SPV as the first argument, add a comma. We give the aspect SPV as the second argument. And we can, that's it. We can pretty much just run it and print. So now it is also a spat raster object, because we're starting with those objects and we're using a function that outputs an object of that type. And I just before, let me just stop for a second here. So the function is called shade, right? I want to come here and do a help shade just to show you guys a little bit more. There is some explanation of what it's doing. And it has here the arguments, right? So if you look here, the default arguments that it is taking is an angle of 45 and a direction of 0 degrees. If we come here on the arguments and we read what that is. So the angle is pretty much the angle of the sun that is coming in. And we can play around with this after we do the first round, so you can see how that changes, but that will change the results. And the direction will also change, which is pretty much the azimuth angle of the light source, also in degrees. So the angle is the elevation angle and the direction is the azimuth angle. So 2 different angles here that are impacting the hillshade. I pretty much, when I don't specify those arguments, I'm just accepting the default values, which we know the default values by coming here on the usage. You can see that it is 45 for angle and 0 for direction. So if we already ran that, and it is a spat raster object. The problem now, and the reason why I like the stars package and stars objects, is because spat raster is not a data set, which makes it very difficult to play with ggplot because ggplot only takes data frames. So let's just bring again now this hill object to a stars format. So to do that, we just add pipe here. And then there's a function that we have been using called st_s_stars. So again, we're going from one raster object to another raster object of different types. And the reason why we change into stars is because stars works nicely with ggplot and spat raster does not. So if we just run that, and then you run the code that I left you for the plot, and you print it, this is the hillshade. So I think this is actually a lot more useful, at least visually, for us to understand what is the topography of this field, right? So we see here like points that are, well, so here in this, actually, let me think, I think we should have, no, I think this is right. So white is on the, is higher levels, and black is like lower levels of hillshade for our settings. But you can really see more of the topographical features of this field when we combine both slope and aspect that were a little bit more difficult to see with them individually, right? And a quick exercise I want to show you here, just for us to play around a little, is if you come back on the hill line of code, let's begin by changing maybe the angle, right? So let's just change the angle argument to 90 perhaps, so 90 degrees. And if we run that, run the code. So now you can see that the values change dramatically. They're way more squeezed as well. But if we see that now, you can still see some of the features of the terrain of this field, but it's a different look than when we had an angle of 45, which was the default, right? So we can really play around with this angle here. Maybe let's try 180. So now it's a little bit more similar to what we were seeing with the 45 degrees. But again, we see that the values here change, right? So it is being impacted by both that elevation angle of the sun and also the azimuth angle.
Could you explain again exactly what it means when you're changing those angles? I'm not sure I followed you exactly. I probably just lost concentration for a moment.
Yeah, so this argument here, angle, is, if we just come back to the documentation again, it is the elevation angle of the light source of the sun, right? So it's pretty much like the way that I'm thinking of it is just like how high that sunlight is coming in and interacting with the terrain, right?
So is that a function of just a time of the day or a season of the year, combination of both? How do we account for that angle?
I don't really, I mean, I guess the short answer is I don't know exactly like how people define when they're showing hillshade. I don't know if I ever ran into somebody explaining like why they selected a given hillshade. I guess from one perspective to think about it is perhaps, it would be to an angle that shows most contrast, I would say, in my head at least, because when we tried the 90 degrees angle, if we just do that again just to show the map, I don't know, it's a little bit more difficult, I guess, to see, even though the features are there, right? The terrain features are not changing, it's just the way that we're visualizing them. So I would select an angle that highlights more easily the features of the terrain. But the fact,
okay, I was trying to make it more complicated than it was. I was thinking it has something to do with the actual position of the sun and so on, but it's really just the best way. That's why they recommend 45 is to see the differences. Basically, you get I guess the most contrast that way.
Yeah, and it's possible that changes from field to field as well, I guess, and maybe angle 180 is actually perhaps is even better than 45 if we look at it, because it makes it really is really showing like the higher points. And then, I mean, perhaps it's similar enough actually, but I think I like actually the 180 better, because we really see there's a depression right there. We see some high points here and where the water is flowing. And we know George already showed us like how those gullies are formed in this field. So yeah, it's just I guess yeah. The answer is I really don't know how, like, if there is a protocol for you to select a given angle. My personal impression is that it would try a few different ones and select the one that highlights better the features you're trying to show.
But I suppose it could be used, back to the comments I made before you described what hillshade does. I guess if you were really trying to see true shading, you could identify the position of the sun at a particular time of the year that you're interested in, and then maybe at noon where it would be, and then you can understand how much solar radiation each part of the field was receiving.
Yeah, that's
But
true.
when we place solar panels in the field, we have to, depending on our latitude, we have to angle the solar panels to get maximum exposure.
Yeah.
We have to orient them towards the, so many degrees south, and the angle of the solar panel itself compared to the ground.
Yeah, that's a great point that, I'm just kind of thinking on the go here as well, because if you're just trying to show terrain features, maybe is not as critical. But if the goal is perhaps to show the effect of that terrain features have on solar radiation, right? Like on how much solar radiation given parts of the field are getting due to terrain, then maybe that number is not as it should be more objective as you're saying.
Yeah, that's interesting.
Yeah, absolutely. And it is also interesting because, again, the terrain is not changing, right? We're just changing our assumptions about the light that's coming and how it's interacting. And something that's happening is the values change of hillshade, right? And of course, like relative to like within this field, those values are all relative. So it's not like I would expect, overall them changing completely, but they are changing according to the light source. And so it's an interesting layer. Well, and also we have only played with angle, right? You can still change the other argument that is called direction. So the default for direction is 0. We could use, let's try, 45 maybe, and see how does that change things. Yeah, so we really see how, on both of the combination of angle and direction. So again, angle is the elevation angle of the light source, and direction is the azimuth angle of the light source, which can be a little bit confusing to really wrap our head of how they're different. But, I guess for our purpose here is more related to just showing the terrain features, or choosing values that better show our terrain features for us to just understand and interpret.
If I'm not mistaken, I think azimuth has to do with the season and the latitude of the place, and then the angle is just the time of the day. So I think because for summer, because of the decline of the planet, it changes how direct is the light source. That's why they call it direction, I guess. I'm not sure, but I think that's the case with azimuth.
I think you're right.
That's a great observation. It's interesting that they don't really explain that in these terms, at least not on the function documentation, but that makes sense. Yeah, it's something that I am interested in reading more and understanding really what do these values mean, because I think here they are.
Dr. Basil, can I add something?
Yeah, there's a yes.
Yeah, if you do view and the function, you can actually look into the function. I was just looking at it, looking at it, and maybe we have some other information here too. So, not here. The function, the shade function. Yeah.
Yep. Shade. Yep. That's right. Yeah, that's a nice.
Yeah.
It's a nice trick. Yeah. So what Sunab was saying or proposed here is if you use the function, so there's a function called view, and if you give it inside this function, you give another function's name, you can actually look into the source code of that function, which right here is that shade function. So they really show how they calculate how it's all happening behind the scenes. Yeah. And I mean, there's lots of like Angular functions here like cosine and sine, and just to really take that angularity of the incoming radiation into account. Yeah, I mean,
so I guess 180 means sunset, right? It should be just the sunset. That's why we had the you could see the high, the top.
I think 180 is the post sunset, right? Exactly, because the light bends, so it's a little earlier than sunset. So
yeah, it's just on the horizon, I guess. That's why.
Yeah, that's right. Yeah, no, and this was a great I guess introduction to how you would look into a function, because another thing that I guess somewhat stems from this conversation is R and Python are open source, right? So there are a couple of things that come with that definition. So one is that they're free, you don't have to pay for them, but also that you can both develop things yourself and make available for others, but also inspect what others have developed, right? So here, as we're seeing this shade function, somebody wrote this function. I don't even know who that person is, but if I really wanted to see what the function is doing behind the scenes, this would be a way of doing that, of just really checking the code, and trying to understand. And this goes for all functions that we're using, right? Like there's nothing in R that you don't know how to see what's going on behind the scenes. It is possible that when you do the view, we come like something very complex comes up that we don't understand. That is possible, but you can still know what's going on behind the scenes, and that's part of one of the reasons why open source programming languages are.
The only bad part about it is that sometimes we get errors that we actually don't know what those parameters are. So you can actually go in and look, or just copy the whole thing and change it according to yourself.
Yeah, absolutely. Yeah. No, that conversation is turned into a different direction, but a really important one that I think is good to have when we're using open source. Yeah. Okay. So let's just decide on. Maybe we can keep direction 0. Well, I guess we can just keep also angle as 45 for now, just so we all have the same values, and just use those. But yeah, just this conversation of the hillshade being a function of both slope aspect as part of the terrain features, but also of how it interacts with light. Okay, so if we just come to our next chunk here, I want to show you guys actually how to make that plot that I share with you on the email. And so this, if you can stay right here, I just want to show you, I'm going to come up all the way to my setup, and I want to show you that we loaded already the patchwork library. So this package called patchwork helps us to combine maps in different ways. And I really like it. I use it a lot for like when I'm writing, putting together presentations, posters, writing manuscripts, when you want to have multiple panels, I use this package a lot in R. So just wanted to highlight that that's what we're going to be using next. So we're right here. So we can just come here, and the way it works is you really just type the object names of the plots. So if you recall, if I'm just going to come up here, we saved this elevation map to an object called a lav map. So if we come back, let me see here. If we come back here, we're basically just going to start giving the names of the plots. So a lav map plus the next one was slope underscore map plus the next one aspect underscore map plus the next one flow direction underscore map plus the last one hillshade underscore map. So these were all objects that we created, and that we created those plots and saved them into these into these object names. So if we just run that and see, it prints very weirdly on our chunk here. You know, it doesn't really look like something I would put in a publication at all. However, I don't know, I don't remember now if I showed you guys already this function here that is called Ggsave. So Ggsave, basically the first argument here, we specify the path that we want to save this figure in this case. And so the path is, we get outside of the code, go inside output, because this is a product of our analysis. So not going in data, going in output. And then we have this terrain.png. So terrain is the name I decided to give it. And then you have to give an extension right here on the name. So Ggsave takes PNG, PDF, JPEG, SVG, and maybe a couple others that I'm missing. But you have to specify that here. I'm using PNG right here. And then I'm defining the width and the height of the plot. And these are in inches. So if we just run this, and if you didn't get any errors, maybe, so you have to have the output folder already created. If you didn't have it, this code is not going to work. But I'm coming here, clicking on that art blue button. I already had the output folder created right there. If you didn't, you can just create new. So once you are in the main directory, you click on new folder and you just write output and it's going to create right there. But if you already have it, you don't have to do that. But once we save this graph on this output folder and we really come here and check, so that's the terrain.png, this is what we see. So we see that the dimensions of the plot are different from what is showing on our chunk here. So the chunk is just like a squished version that does not represent how it will look when it's saved. So it's always great to check the saved version and not the chunk version when you really want to export a figure. So this is our figure. We can see all of them together. We see that Patchwork basically just placed them in the order that we gave those object names. Yeah, so this, you know, of course, like if this was really going in a publication, there were a few things that I would still add. So like a scale and a north arrow, and add the letters A, B, C, D. Those would be things that would make these plots publication ready, pretty much.
Leo, you may have covered this last time, but why is the unit of slope radian instead of percent?
Yeah, that's, thanks for bringing that up again, George. So I originally had, I think the default for those using the function terrain is degrees. And I left as degrees to begin with. But the thing is that on the shade function, so the one that we used to do the hillshade, it takes a slope and aspect, but they have to be as radians.
I see. Okay.
Yeah, so that's why I decided to do radian. But that's a good point, because you know it's probably not common to report slope and aspect in that unit of radian. So if this was, you know, if we were putting this together for something official that you're presenting somewhere, what I would do is basically create the versions of slope and aspect when we created them. So going all the way back here, I would basically create two versions. One that would be in degrees, and that would be the one that would actually make a plot and show. So aspect in degrees and slope in degrees. And I would also have to create the version in radians just so it would work nicely when we do the hillshade.
What I don't understand, so So radians for aspect, I think makes a lot of sense to me because it's just another way of reporting an angle, but a slope is not the degree of a slope. What I thought we were doing here was physically rise over run. Is that not it? That's not reported in radians, right? That doesn't make any sense. Is this a different way we're looking at slope than what I understood?
So my understanding of the function slope is that it's going to give you a degree regardless. And I think it's doing that basically because comparing that pixel with the neighboring pixels. And so it's just looking at that degree difference or the degree of comparing one pixel with its neighbors.
So it's a geographic measure of slope rather than a physical, like, slope like this.
Right.
Make it look on Zoom.
Yeah. Well, because I guess like a slope could also be meters, right? Or like a metric that way.
Yeah, I'm not familiar with that. Maybe you can explain that to us a little bit because I think most people are thinking of slope the way I'm thinking of slope.
Yeah, maybe the best way for us to really see what this function is doing is just by checking to see if that terrain function is giving us any more explanation about that. Of how it is calculating or how it is really using zero. Let's see if it's telling us anything. Yeah, I can do more. So I don't have the quick answer to that, but I'll do some more reading and I'll report back to you guys so we really get that understanding of why this is in degrees and not a different unit. So I'll get back to you guys on that.
Yeah, this is really interesting. I'm not trying to cause confusion here, but I think of at least Emily and Sunab could be using this in their research. So it'd be great to have sort of a better understanding on their part of, and you two can do some more reading on this on your own and maybe report back to us rather than asking Dr. Bastos to do it. You two can do it.
Maybe I'll do for sure, and anyone else that's interested can also do because I agree that they can be a little bit confusing, and so it's definitely great to refresh on that as well.
Yeah, perfect.
Yeah, awesome. Okay, so we are after. Well, is it okay? I mean, I guess we're just going to keep going a little bit more because we just have really one more chunk that we're.
Yeah, let's just, if you're available, let's just do it on Wednesday so we're not rushed and everybody can participate. Because I know some of the students have to run to class. So if you're available Wednesday, we can just do it on Wednesday.
That's true. We can do that on Wednesday then. And then, and also just to let you know, so I will be posting another script, which is the one for soil electroconductivity, which we're gonna finish this on Wednesday and then start and hopefully finish the soil EC one on Wednesday as well. And then at that point, we're gonna have all the layers that I wanted to show you guys before we actually got into any type of clustering and zone management creation. So that's probably gonna be then for Friday. We'll
Perfect.
start
that sounds great.
All right.
Thank
Awesome.
you.
Thanks, everyone.